In this part, I would like to discuss the Blake and Scholes option pricing model. Okay, now I would like to introduce the Blake and Scholes option pricing model to you. It was introduced in 1973 by two authors, Fisher Blake and Merron Scholes, one of the most prominent figures in the finance discipline, and their formula for pricing European call and put options on non-dividend paying stocks was probably the most famous model of the modern finance. It is relatively easy to use, and it is an adequate approximation to the price of more complicated options. The formula at the top of my slide is given. It's a O sub C equal to ND1 times P minus ND2 times present value of EX. There ND1 and ND2 represents the probabilities that a stock price and its exercise price will be relevant. That is, call option finishes in the money at expiration date. As I explained, O sub C is a call option price, P is a stock price, ND1 is a cumulative normal density function of D1, PV of EX, present value of exercise or strike price, ND2 equivalent to cumulative normal density function of T2. Later on we will be using R, which is a discount rate, and it is 90-day commercial paper rate or risk-free rate. T would be the time to maturity of an option, will be given as a percentage of year. V represents the volatility, which is the analyzed standard deviation of the daily returns. Now we need to shed more light on ND1 and ND2. What ND1 is actually the probability that a normally distributed variable will be less than D1 standard errors above mean. If D1 is large, then ND1 will approach 1, meaning that you can be almost certain that the variable will be less than D1 standard deviations above the mean. If D1 is 0, then the normal distribution of D1 will be 0.5, meaning that there is a 50% chance that a normally distributed variable will be below the average. If D1 is negative, then ND1 will be less than 0.5, meaning that there is a less than 50% chance that a normally distributed variable will be less than D1 standard deviations below the mean. Simplest way of finding ND1 and ND2 would be using the norm dist functions from the Microsoft Excel. You can use this function both for the positive and negative D value or D numbers, and these normal distribution values can also be obtained from the tables given at the end of different textbooks. For the inputs to the Blake and Scholes formula, we need to find out the present value of exercise price, which will be equivalent to exercise price times e power minus RT, which is continuously compounding, whereas the D1 values would be given by the expression where the log of the stock price to exercise price plus risk-free rate plus the fraction of volatility squared divided by 2 into T. This numerator expression is divided by the volatility times square root of time to expiration. This will give you the value of D1, whereas the D2 would be simply the one's value minus volatility times square root of T. This is how we get the inputs for the Blake and Scholes formula. Through this slide, I would like to let you know how to make calculations to get to the option value using the Blake and Scholes pricing model. In this example, we have been given certain inputs. to find out the price of call option. These inputs include the price of a stock that is equal to $36. Risk-free rate is 10%. Volatility is given 0.40. Exercise price is $40. Time to expiration is 90 days, which would be fraction of 365 days. We'll use the expression for D1, and using inputs we'll get the we got the D1 equal to minus 0.3070, and its cumulative normal distribution value would be about 0.3794. For D2, value would be D1 minus V into square root of T. That value is equal to minus 0.5056. If you go and find out ND2, this value would be 0.3065. Once we find out ND1, ND2 values, and we find out, then we go and find out the option price by inserting these values for ND1 0.3794 into price of the stock 36. This portion minus the ND2 value times strike price times the e power minus 10, which is a risk rate, times the time to expiration, which is a ratio of 90 days to 365, and we get to the call option price, that is O sub C, equivalent to $1.70. Up to this point, according to Black and Scholes model, there are 6 factors that determine the call option value and the put option value. These factors are variables or affecting call and put prices. First one is the increase in underlying asset value. That would means underlying stock price. If that is positive, that will have a positive impact, means with an increase in underlying asset value there will be increase in the call value. This means the higher the current value of underlying assets, the higher will be the value of right to buy them at the fixed price. Second one is a strike or exercise price. If there is an increase in a strike price, there will be a decrease in the call value. It is obvious that the higher the exercise price, more expensive is to exercise your right, and when P finishes in the money. Third is the volatility of the stock returns. If there is an increase in variance of underlying assets, that will also increase the call value. This means the higher the variance of the underlying asset, there will be higher potential gains from the price movement. This is a special nature of option securities. Third is the volatility of stock returns. From this perspective, if there is an increase in the variance of underlying assets, there will be increase in the call value. We can understand it as there is a higher variance of the underlying stock, there will be higher potential gain from the price movement. And this is a special nature of option securities. And then we have time to option expiration. It also have a positive impact. That means if there is increase in time to expiration, there will be increase in the call value. It means longer time left, higher the chance we get to the exercise the right in the favorable in the money situation outcome. And the fifth one is risk-free rate, interest rate corresponding to the life of option, and it also have a positive impact. If there is increase in interest rate, there will be increase in the call value. One can think of it as the interest rate you earn from the saving up the money to exercise right in the future. With that higher the interest rate, less you have to set such fund aside to begin with. Notice that risk-free rate is used because we wish to be more certain about having such money needed to exercising the right. The last one is the dividends paid on the underlying assets. Dividends increase has a negative impact on the call value, and call value decreases. We can understand that the value of underlying asset can be expected to decrease if dividends payments are made on asset during the life of an option. Consequently, the value of call on asset is decreasing function of the size of expected dividend payments, and the value of put on the contrary is increasing function of expected dividend payments. From the put value perspective, some easy to memorize tips would be that only two factors are the same as for the call, that is volatility and time to expiration, and rest are simply reversed. Now it's also important for us to note a few assumptions that can undermine the validity of Black and Scholes model application in calculating the call option price. And first one is the dividends. Black and Scholes model is built on the dividend protected case. That is, there's no dividend paying for the underlying stocks. Payment of the dividends, not to be confused with the announcement of dividends increase. The payment of dividend reduces the stock price and thus reduce the potential gain from exercising the call option. The adjustment can be made by the dividend yield discount factor for the variable P. The call option price would become in this case O sub C equal to ND1 times P naught into the continuously compounding factor e power minus y into T. This first part is incorporating the adjustment for the dividend factor, where the part that is added as a dividend yield discount factor. Dividend yield is denoted by y, and it is the ratio of the dividend payment over the current price, current stock price. Second factor is the early exercise. Keep in mind that the Black and Scholes is originally designed for the European options, where exercise can take place at any expiration date. Mostly we deal with the American options, where early exercise is possible. One of the ways is to use modified version of binary models. Last topic of this part 2 of real option analysis in explaining the basics of the option pricing is the put call parity. Put call parity is a principle that defines the relationship between price of European put option and European call options of the same clause that should have a same underlying asset, stock price, and expiration date. It can be shown that the two investment strategies below produce identical payoffs in all scenarios of price movements. First one is a buy call, invest present value of exercise price in risk-free asset. Second one is a buy put and buy share. As a result, to prevent arbitrage opportunities, two strategies must have the same value in the market. So value of call plus the present value of exercise should equal to value of put plus the share price. If you rearrange, and we will get value of put would equal to value of call plus the present value of exercise minus share price. So this is also giving a way to pricing the put option. The value of call can be obtained from the Black and Scholes model, and present value of exercise prices is as a discounted by the risk-free rate. So this will help in getting the pricing of the put option too. At the end, I would say up to this point we should be somehow ready to discuss the calculations of real option values. We will look at how three types of real options will be revalued separately using the Black and Scholes option pricing formula. These real options include option to expand, option to delay or defer, and third one is option to abandon. So stay tuned, and we will look into the detailed explanation of these three real options in next 3 videos. Thank you very much for listening to me.